All right, here we are. 7.3, another day, another dollar. The slides are going to get a little bit shorter from here. We've kind of gotten over the hump in that sense. Instead of a barrage of 50 problems, we're going to do a lot less quantity and sort of more quality. So we're going to start kind of really focusing in. 7.3, we'll see, just has a quick fill in the blank problem. Has kind of just like a very generic kind of no context type application of the central limit theorem. Central limit theorem is what 7.3 is all about, and then 3 word problems. And if we can do all of those, I think we're in pretty good shape for where we need to be. All right, so this was like a fill in the blank. The bold-faced thing is what actually fills the blank in. So the question is, the blank states that the sampling distribution of x bar, right, that's just the sample mean, is approximately normal when the sample is large. That's what the central limit theorem says, right? Central limit theorem, most important theorem in all of statistics. Actually, you know what would be a fun, I just thought of this now, you know what would be a fun kind of homework problem is write your own, oh man, how about this? If you want to do this on your next test, I'm not promising you any extra credit, but you never know. You never know what kind of mood I might be in. What if you were to write your own fill in the blank question in which the answer is the central limit theorem? So maybe you would write the blank is the most important theorem in all of statistics. That's pretty cool, right? Or blank is even more miraculous than a baby being born during a sunrise. Yeah, that's true, right? We already talked about all that. So we're well acquainted with central limit theorem, TLC backwards, all that stuff. Oh yeah, TLC blank is TLC backwards. Oh, that'd be a fun fill in the blank question. So I'll leave it to you. Maybe you can kind of sketch out some of your own. I'm kind of excited to see what you might come up with. So here's number 9. So number 9 is just kind of this little generic problem. Kind of it allows us, generic problems I think have a role pedagogically. Right, they kind of strip away some of the cognitive pressure that word problems can induce and allow us to kind of just drill down and focus just on mechanical applications. So the book says a sample of size 75 is drawn from a population with a mean of 10 and a standard deviation of 12. All the other bullet points are kind of like my thought process. So the first thing I see is I say, okay, I've taken a sample. If I read ahead, the question asks questions about the sample mean. So the central limit theorem tells me a few things. The central limit theorem guarantees a few facts. Fact 1, the mean of the sample mean is the original mean, so that's 10. Fact 2, the standard deviation of the sample mean is the original standard deviation divided by the square root of the sample size. So that is, right, we take that 12, we divide it by the square root of 75. Make sure you punch this in your calculator yourself, because this is one of those things that's actually surprisingly tricky to do in a calculator. And the last thing you want to do is actually find out on test day that you're not quite sure how to do it correctly. So make sure you type that in and verify that you get the same 1.39 that I did. And fact 3, right, since the sample size is 30 or more, right, the central limit theorem tells us that we can think of the sample mean as being approximately normal. Why do we care about approximately normal? Because that means we can use normal CDF. That means that we can use inverse norm. It means that all that stuff that we've been practicing over and over and over and over is applicable to any question involving the sample mean. So those are the only 3 facts that we need, right? Fact 3 tells us we can use normal CDF. Normal CDF requires the mean and the standard deviation. But we can get both of those from facts 1 and 2. So question A, what's the probability that x bar, the sample mean, is going to be between 8 and 14? Well, x bar follows a normal distribution, so I use normal CDF. I want between 8 and 14, so I put 8 as my left bound, 14 as my right bound. And, right, the facts from the previous slide tell us the mean is 10 and the standard deviation is 1.39. Really? This is just like all the problems we did before. The extra complexity is just that, right? We have to transform that standard deviation. When we're working with the sample mean, the standard deviation always shrinks by this factor of square root over n. And then it asks us the 15th percentile of the sample mean of x bar. Well, percentiles are just inverse norm. So inverse norm, PMS, right? Percentile mean standard deviation. We plug all that into our calculator. I suspect that you could do this in your sleep. In fact, who knows? Who knows? Maybe your spouse, your boyfriend, your girlfriend, your roommate, your pet is complaining that you actually are doing this in your sleep. There's worse things we could be doing, I suppose. And that's it. Done and done. So let's try some word problems. So problem number 21. We're interested in the average gas mileage of a fleet of 60 cars. So, right, you run like a car rental business, I guess, and you've got 60 cars. So you're trying to kind of get a sense of, right, how much what their gas mileage is. Again, before we solve the problem, if you read ahead, involves sample means. Anytime something involves the sample mean, that's like a red flag. That makes me think central limit theorem. Anytime I think central limit theorem, I'm thinking about the following three facts. The mean of the sample means the original mean, so that's the 28. I didn't write it in the slide, but if you read through the actual problem from your textbook, you'll see that it's 28 is the mean. The standard deviation is the original standard deviation. The book tells us that's 3 divided by the square root of our sample size, so we do that. We should get 0.39, and since the sample size is more than 30, the sample mean is approximately normal. Thanks, central limit theorem. Also, side fact, remember, I don't know that this comes into play with any of the problems that the book assigns us, but it is also a fact of the central limit theorem that the sample mean is normal for any sample size if the underlying distribution is normal. And of course, in real life, that's seldom the case. So in real life, we're usually looking for 30 or more. But I think sometimes I do put a test question on a test that actually highlights that there's actually 2 conditions. You only need one of those 2 to be satisfied. Either the underlying distribution is normal or your sample size is more than 30 for the central limit theorem to sort of kick in. And then once we have those facts, we could just apply them to a bunch of problems, right? So what's the probability the sample means more than 27.5? What's the probability the sample means between 27 and 27.8? What's the probability that the sample means less than 27? Yeah, cool stuff, right? And then I kind of just added, I think I just added a little something there. So I mean, it would be very unusual, wouldn't it? So that's basically saying for our fleet of 60 cars, it's very unusual, in fact, almost impossible, only 0.5% chance that the average gas mileage would be 27 or less. So why do we care? Well, again, that's what we're thinking about, right? We're learning this stuff for a reason. We're learning this stuff because, right, statistics is not just some hoop to jump through to get your degree. Statistics is a useful, dare I say, critical way of being able to look at the world, to use data to solve interesting real world problems. So why do we care about something like this? Well, because if we actually saw a sample mean, right? If we had our 60 cars and we put them all out there and we recorded the gas mileage after their use, and the gas mileage, the average gas mileage was less than 27, well, that shouldn't really happen. Right? There's only a 0.0052 chance of that happening, a 0.5% chance. So if it did happen, that might be a little bit of a red flag to me that something's wrong, right? That might be an indicator that maybe it's time to inspect the fleet. Maybe it's time to send the fleet to the mechanics. Maybe the fleet is overdue for their inspection, right? It's potentially indicative of something being wrong, right? That we literally saying it was unusual for it to be 27 or less. So if that were to happen, our follow-up question is why? Why is something unexpected happening? And what should we do about it? Although it occurs to me now that I guess actually having a gas mileage, no, I take that back. Anyway, a low gas mileage, it's one of those tricky things. Low gas mileage is bad. We want high gas mileage. So yeah, so if we were seeing a low of something 27 or lower, that would be potentially bad and maybe something we would want to look at. Yeah, so all right, new problem. TV sets. Again, the textbook kind of sketches it out, talks about the average number of TVs that that a U.S. household has. So right, apparently on average, a house has 2.24 televisions. Go figure. And we're going to ask some questions about X bar, the sample mean. Anytime I see X bar, the sample mean, my brain thinks central limit theorem. Anytime I think central limit theorem, I think about the following three facts. Fact 1, fact 2, fact 3. Those same facts, I'm just cut and pasting them. The mean is the same as before. The standard deviation is the original standard deviation over the square root of the sample size. As long as my sample is large enough or the underlying distribution's normal, the sample mean is approximately normal. Why do we care about that? Well, that's what justifies us using normal, CDF, and inverse norm on our calculators. And there's all our answers, right? Probability that it's that a household has 2 or more TVs. Probability household on average, so the average amount of households, the average number of TVs in 85 households, sorry, is between 2.5 and 3. That's about 2%. Find the 30th percentile. Let's see here. Number D, would it be unusual for it to be less than 2? Oh yeah, and I observed that this actually is just 1 minus number A, so hopefully that makes a little bit of sense to you. And then that whole idea of is it unusual? So we solve, it's 42%, so we'd say it's actually not unusual. Oh, interesting. Actually, it occurs to me. No, I did it right. So actually, so notice that number E actually does have a little bit of a wrinkle there. So number E does say, can you tell whether it would be unusual for an individual household? So now we're not dealing with 85 households. It says an individual household to have fewer than 2 television sets. So now we're working with just a single observation. So that's why if you notice, I use the original 1.2 standard deviation. You could almost think of it as like a sample size of 1, right? And so, right, we take the original standard deviation 1.2 divide by the square root of 1, it doesn't really change it. And I calculate that. So it's kind of a little bit of compare and contrast, right? So we're basically saying that it would be unusual if you took a sample of 85 houses for the average number of TVs to be less than 2. In fact, that's unlikely to happen. There's only a 3% chance of that happening. However, there's a 42% chance if you just picked one household that household would have 2 or fewer televisions. Again, it's kind of like the radon problem from the previous section. It's just a reflection of the well, if we're talking about E, the larger standard deviation, kind of meaning less precision, and of course reflected in in this case, a larger probability. So I think there's one more problem. I can't think of the number of it off the top of my head. but it should be in the syllabus. So go ahead and pause it if you haven't already solved that problem, and then we'll compare answers. Cereal. Cereal sounds good to me. So number 33, we're working with some boxes of cereal. We're going to talk about sample means. So again, right, we look at the facts, right? Fact one, the mean is the original mean. So we're told that that a box of cereal weighs 12 ounces. Now again, when a consumer tells you, not a consumer, when a manufacturer tells you that a box of cereal weighs 12 ounces, again, they're not guaranteeing that every box of cereal is going to dead on weigh exactly 12 ounces. They cannot have that level of precision. Sometimes a box weighs a little bit more than 12 ounces, lucky you. Sometimes a box weighs a little less than 12 ounces, unlucky you. They're just claiming on average their boxes weigh 12 ounces. And it turns out, right, there's a certain amount of variability about that mean. Here, that variability is 0.1 ounce. And then the book goes on and asks us some questions about average amounts. If we take a sample of 75 boxes and we look at right, the average weight of that sample, it asks us some questions. So again, I see a sample mean, I see an X bar, I think central limit theorem. I think central limit theorem, I think the following three facts. The mean of the sample mean is the original mean. The standard deviation of the sample mean is the original standard deviation divided by the square root of the sample size. So 0.1 divided by square root of 75. And since the sample size is more than 30, the sample mean is approximately normal, which means we're justified using normal CDF and inverse norm. All right, so the book goes on and says, all right, if the claim was true and you found an average of 11.99s, would that be unusual? And we say, no, it's not unusual. And then C says, all right, if the mean weight of the boxes were 11.99 ounces, would you be convinced that it's false? So not really, right? So 11.99, we saw something that small or less is a 15.87% chance. So we would say that's actually pretty consistent with their claim, at least using our books kind of criteria that we think of like 5% as being unusual, not unusual, consistent, not consistent. And I think it just repeats this for instead of 11.99, 11.97. So here we do the calculations for 11.97. We get a very small number, like 0.1%. That's certainly much less than 5%, so we would say it's small or surprising. And so, right, here, right, and this is kind of like, this is actually like an important, part C is important. I want you to kind of think through the logic of part C. As we move on, so I mean, we're essentially finishing chapter 7. We're moving into chapter 8. Chapter 8 is part of a larger section on what's called statistical inference. And we're going to do a lot of kind of applying statistics, really applying the central limit theorem to kind of come up with claims along the lines of C. So if someone told us that the mean weight is 12, and we took a sample of 75 boxes, we measured all the weight of all those boxes, looked at the average weight, and we found it was 11.97, which in theory doesn't feel like it's that far off from 12, right? I mean, 12 ounces, 11.97 ounces, those numbers actually seem really close to each other. However, what we've just shown in part A is that if the mean really is 12, that's what we plugged into the calculator, if the mean really is 12, it's almost impossible to see a sample mean of 11.97 or smaller. So if we actually did take a sample and see a sample mean 11.97 or smaller, we would say that that's inconsistent with the claim of an average weight of 12 ounces. Why is it inconsistent? Because if it really was 12 ounces, the mean really is 12 ounces, it's almost impossible. There's only a 0.1% chance of seeing a sample mean as small as 11.97 or smaller. So if we actually saw something like that, that would make us doubt the claim of the manufacturer. Something to reflect upon as we put chapter 7 behind us, and an idea that we will continue to explore in a greater level of explicitity and and repetition in the upcoming chapters.